Good afternoon, everyone. Welcome to the Samvaad talk. Today's talk is on advanced memcomputing devices by Professor Ananda Vaya. To give a brief introduction about Ananda, Ananda Vaya completed his PhD in 2023 from the Department of Electronics and Electrical Engineering, IIT Guwahati. He obtained a BE degree in Electronics and Communication and an MTech degree in VLSI Design and Embedded System from Visvesvaraya Technological University, Karnataka in 2011 and 2014, respectively. Before starting his PhD, he worked as an assistant professor at the Department of Electronics and Communication, the Ananda College of Engineering, Bangalore. Additionally, he served as a JRF in a DST SERB sponsored project titled Performance and Energy Optimization in Many Core Processors using Dynamic Operation Cache Memory, NOC and DRAM controller at the Department of Computer Science and Engineering, IIT Guwahati from 2017 to 2018. His research interests include Memcomputing devices, memelements, analog and mixed signal integrated circuit design, semiconductor devices, digital circuit design, FPGA implementation, and VLSI architecture. Welcome, Dr.
Thank you, Professor Kurian, for your brief introduction. So, firstly, good afternoon, everyone. So, in this Samvaad talk, I welcome you all to gain some insights about this advanced memcomputing devices. So, we'll start the presentation, start from introduction, then we will know about what are the three important memcomputing devices like Memristor, meminductor, memcapacitor, and also I will go to share some of my work previously what I have done. And so you're already most familiar with whenever you go to study computer architecture or any VLSI. So we're already familiar with Moore's law. So Moore's law, you already know that every 18 months the size of the transistor getting reduced so that the total number of transistors increased to 2 times. So if you keep scaling down the transistors, you already know a lot of limitations and a lot of challenges and difficulties right now what we are facing using the current conventional CMOS devices, and leads to power dissipation, high power dissipation, subthreshold effects, and other nonlinear effects. So there are a lot of limitations in Moore's law. So, and also, so when we will go for high performance, data intensive, and performance critical applications. So today's modern conventional processor not support much because as we all already experienced that problem, like so you have a lot of huge power dissipations and there are a lot of other problems are also so time consuming. So looking into that all these issues, so no, right now we are looking towards brain inspired computing, neuromorphic computing, and other high performance computing architectures. We look for much more robust and resilient devices so that it will support this kind of applications. And we're starting doing research on a lot of other areas like artificial intelligence, edge computing, brain machine interface, and a lot of other high performance computing applications. So we need, it's a alarming time for us to look for new devices that will support this kind of applications. So likely, so we're already familiar with these fundamental devices like resistor, inductor, and capacitor. We're already familiar. These are all linear devices. And based on the relationship between the fundamental electrical quantities like flux, charge, voltage, and current, we already know that. But so there is a missing link between flux and the charge. So which leads to the arrival of new device. That's what we call Memristor, which has been firstly discovered by this the professor named called Lian from University of Berkeley, 1971. So based on this relationship, so he came out with a new device. So that is what we call it as a Memristor. So we will see that what exactly this Memristor and how exactly it will work and why we need this kind of devices for high performance computing applications and all. So these are all the things how we will got to know about this Memristor, start from the way back to the several decades back. So we will come to know about this negative resistance devices and also the metal oxide devices and everything. And around 1967, they will explain about the important phenomenon of this titanium dioxide and thin film, which exhibits important properties. So later, Lian 71, he come to know about based on this earlier behavior of these devices. He noticed the important characteristics. So then he realized this new device, that is what we call it as Memristor. So later into the around 2008, so the team from HP Labs, so they are first time they have discovered, and also they are they are stated that there will be an existence of new device, so that is what we call it as Memristor. So then later on, it giving a lot of motivation to researcher and other scientists to look more into this kind of devices because of its very phenomenal, interesting properties. So you can see the simple definition of this the Memristor and everything. So I already told it is based on the relationship between the flux and the charge. If you take the time rate of this flux and the charge, ultimately it leads to the unit of ohms. So that is what we call it as. It is also kind of resistor, but it is not like exactly like resistors. So then what is the difference between this resistor and this Memristor? So resistor, we already know it is simple linear element. So based on the current and the voltage, it's keep constant. So that is what we all know that. But Memristor is not like that. Memristor is also it's having its own phenomenon called it's combining the memory property also. And at the same time, the Memristor, this new device exhibits a very important property, that is what we call as a nonlinear property. And another important property, what we call it as non-volatile property. We will see that what exactly it is. So this is what this is how we will go to evolve with this new Memristor. So that is the base. It will the Memristor behavior keep changing its behavior based on the quantity of the charge. So that's how it will keep retaining its previous history. Then it will exhibits this non-volatile property. So these are some of the interesting properties. Then we will see that why we have to know more about this new device. Firstly, we will see how exactly it will we will this non-volatile storage and how it will use this non-volatile property. And also another important, most important property of the Memristor, as most of them already know that. So whenever we will go to use the conventional devices right now, so like a CMOS device, if you take, so it is purely based on what PN junction theory, right? So whenever we will discuss about PN junction, there is always a interface between the P-type semiconductor and N-type semiconductor, isn't it? So then there is whenever there is a recombination of this majority charge carriers happens, so there are chances that the minority carriers will store in this junction. So that leads to the leakage of this minority charge carriers. So the junction is the root cause for this kind of like leakage, power dissipation, and everything. But while come to the structure of the Memristor, I will tell you that later. It is almost like a junctionless device. If junction is not there, in the sense that there is no less chance for static power dissipation, correct, right? Because there were no chance for the charge to be stored in the junction. So it means junctionless. It means that it clearly shows that it is having a very almost like zero static power dissipation. So that is the best part of this Memristor. And also another important property of this Memristor is it is highly scalable. Scalable in the sense, when you are reducing the size of this Memristor, so it is not compromising with its performance. Even the performance even get better. But in case of CMOS, so if you keep scaling down the device, we are facing a lot of limitations and a lot of challenges. We need to handle a lot of power dissipation and many things. So that is what this is why this Memristor is going to be more required advanced computing device for future electronic applications. And this is what scalability, because the junction is almost zero, so having very good switching speed also. And also, and another important property, whenever I will discuss about this new device, in the sense that we can't completely ignore the conventional devices. Obviously, conventional devices are very much required for us, because most of we can't find all the kind of operation in one device, right? So some operation we will not find in this kind of devices, but in conventional devices we will find that kind of properties. But that's why some operation we will retain these conventional devices, but most of the places we will go to replace with these new devices. So that's why this device is also very much compatibility with CMOS technology. So we don't have any issues when we will go to combine both the Memristor and CMOS technology. We don't have any problem. So that is how it will gives another property called compatibility with CMOS technology. And so now we'll come to the core part of this device. So the one of the focal point of this Memristor device is you've already heard about the term logic in memory operation or process in memory operation, correct, right? Computation in memory. These are all like we already heard about that in most of the advanced computing architecture. So this is what they are all discussing about, right? So this is one of the key property of this Memristor. So Memristor is a device, so it is almost the structure. I will show you that structure also. It is more or less like looks like it's very much similar to the basic functional unit of our brain called synapse. Synapse is just nothing but a connection between the two neurons. Like it is having a gap, like a kind of insulator. Even Memristor also have the same kind of structure in the sense that metal, insulator, metal. So meme structure. So it leads to the almost like mimicking the behavior of that synapse. So that's how we got this property called logic in memory operation. Even our brain is also functioning like that. It will process and memorize within itself. So that is the key property. So that property can be noticed more prominently in this device. So that's why this new device, why we need to focus more about working on towards this new device for advanced computing architecture. So that we will see. Okay. So this is what the problem right now we are facing, one Neumann architecture, right? So whenever we will go to discuss about computer architecture, obviously CPU will be there, memory will be there. So your processor, most of the time it will go to memory and get the data, and there are a lot of latency, and memory and CPU access time will be more. So then that problem we call it as, in technical sense, we call it as memory wall problem, and also in other way we call it as one Neumann bottleneck. In the sense that we will go to use the same address and data bus for accessing the instruction as well as data. So it leads to that kind of delay. So that is the main problem with the conventional technology. And that is the main major bottleneck. But while it comes to in-memory computing, you can see the comparison. So what is the difference between in-memory computing and conventional computing? Right now, what we are using the architecture. So here you can look conventional one. Conventional one have a separate processing unit and separate memory unit, right? So in processing unit consists of control unit and data path like ALU. So you just imagine if this part of ALU is already there in this memory itself, so then how much space we can reduce and how much performance can be improved. So that is what we got that concept called in-memory operation by using this Memristor. So that is this pictorial representation gives the complete details about what exactly this in-memory operation. So we'll see this. So in the sense that we will go to replace this processing unit within inside the memory itself. So it is nothing but a crossbar array. So that I will show you that crossbar array also later. So this is what briefly about this in-memory computing is nothing but computation and memory happening in the same device. So that is what the concept of this in-memory operation by using this Memristor. So right now, so we are already familiar with this conventional CMOS design while designing the basic logic gates and Boolean function and everything, right? So say for example, Memristor is also very much, it will support for designing this digital circuit also. But what is the advantage of using this Memristor? Already told, Memristor is highly scalable. Even if you go below 10 nanometer, it doesn't have any issues. So taking the advantages of that. So we will go to replace this kind of conventional Boolean function using CMOS or CMOS logic circuits using this Memristor. Then what are all the things we can achieve? So firstly, say for example, if you just design on NAND gate, how many MOSFETs are required? Just one design on NAND gate. How many in CMOS logic? How many MOSFETs? 4, right? Four transistors are required. But the size of the transistor is also very high, right? So you just assume in case if I will go to realize the same thing using Memristor, I just required only 2, that 2 below 10 nanometer. If you then think about the size and the complexity and also the power, everything will be more better as compared to what conventional technology. So this is what if you use this kind of technology, these new Memcomputing devices. So these are all things we will go to achieve, and we will drastically reduce the hardware complexity. That is what we are facing right now. We are using conventional devices. So this is what another we'll see. Right now we are all very much involved in the work like deep learning, machine learning, artificial neural networks, spiking neural networks, multi-layer neural network. There are a lot of computation intensive and performance critical application we are already working on. But at the same time, if you look at the hardware complexity also, when you are working with a large amount of data, obviously hardware complexity is also very high, right? So then if hardware complexity comes into the picture, the power, area, everything will be very huge. It is very difficult to tackle. You just have a look at the server room, how many ACs we have kept to cooling down that server, and we have putting extra space and extra money for just to maintain this temperature itself. So it is a very cost effective, very cost intensive also. This modern, this conventional technology, it takes a lot of economy. So that is the main problem with the conventional one. Already told, Memristor is having this kind of behavior, like almost like zero static power dissipation, right? So so it will reduce this power heat dissipation, and also we no need to we no need to invest any extra money for this maintaining this temperature like cooling AC. So that also we will need to reduce. So that is the major advantages of this Memristor device. So and another you can see this the brain. So this is how your brain will looks and how our brain will work. Like these are the important important characteristics of your brain. So it is like more or less like parallelized computing, co-located memory and logic, in the sense that synapse itself, like it will take the data, process it, and store it there, store it back there. So that is what the inspiration. Same kind of analogy we can same kind of realization we can notice in this Memristor device also. So that will support much better as compared to conventional devices. So that in most of this deep learning neural network and other AI based applications, so we can easily use this kind of new devices because of its phenomenal behavior. So that is what the advantage. No, we'll come to the non-volatile memory. I already told this device is just not like a device. It is an intelligent device. It's like an intelligent machine. It means that it will process and store. It means that it has its own intelligence, right? So then, so storing is also one of the important property. Processing is also another property. Now we will come to the storing behavior of this Memristor. So it exhibits non-volatile characteristics. So right now we already know that what about conventional memory we are using, like NAND flash and UV RAM and everything. So and you can think about the area and present how much area it consumes, present memories and everything. So because of its large size and power dissipation and everything. So in 2008, HP Lab had described ReRAM devices. Already told. So 2008, so they discovered the existence of this Memristor. So then onwards, they described about this Memristor and its very much importance for designing new kind of memory. That is what we call it as a RAM, ReRAM. ReRAM in the sense resistive RAM. So because Memristor is nothing but a combination of memory with resistor. It will store the information in the form of resistive state. I will explain that. What is the advantages of that resistive state and everything later. So just have a look. So then in 2015 onwards, 3D memory and everything came into picture. And one of the important memory, the kind of memory is like a crossbar architecture. So that will support 3D ReRAM. So that we will see. So this is what the difference, DRAM and flash memory. And you can see the complexity also. And what are the drawback of this kind of memory right now we are using and flash memory. So we need to fabricate this floating gate. So there is separate after, conventional MOSFET you already know, the gate polysilicon you already know, the insulating layer will be there. So within that we will go to place this floating gate. So depending on the trapped electron, it will store and set or reset the data. So there are a lot of complexity will be there for fabricating this kind of memories and everything. So I will not go more technical detail because you're already familiar with this kind of memories earlier. Now we will come to Memristor kind of memory. That is nothing but ReRAM, resistive. So we look at the structure and compare with the flash memory, this kind of memory, and with this one. Which one is more complex and which one is take more fabrication process? Because just by this picture itself, we can see the structure of Memristor. It is very simple. Having top electrode, bottom electrode, middle insulating layer. So it is very simple. But you can see the flash memory, the complexity, and the fabrication steps we required, and think about the cost and everything, right? So this is what the difficulties we are facing in the conventional memory technology. But if you use this simple ReRAM structure and with it will support what? Very high density memory, right? Because the size will be small, the complexity of the fabrication is very simple. Then obviously, so I can create more dense memory. So that is what we call it as ultra dense memory using this ReRAM memory. So that will be, and also that will be more compatible with the CMOS technology, and it will retain the data for longer duration as compared to this flash memory and everything. I will show it in the table also later. So you will see this, how this ReRAM work, this Memristor work as RAM or memory. So already told, so there is a top electrode and bottom electrode. In the middle, there is an insulating layer, right? So then we need to concentrate on how it will store logic 0 and how it will store logic 1. So simple. It is depending on the application of the voltage only. So So because the insulating layer will be there, so it will create a channel between the top electrode and bottom electrode. I will not go more material details of this. I will simply explain that. So because it's like whenever there is a connection between the top electrode and bottom electrode, depending on the applied voltage, so it forms a kind of channel that we call it as a electrochemical filament, formation of electrochemical filament. If you explain it in terms of conventional, it is a channel, or if you explain it in terms of in Memristor, it is a electrochemical filament has been formed in the when you apply suitable voltage, so that it will store logic high. When you will rupture or remove that filament by applying some other negative voltage or reverse bias voltage, you call it as like that. So it will remove that conduction, so that will store logic 0. So this is how this it will behave like a set resistance and reset resistance. I will explain this LRS and HRS state later. Now this is how the characterization you can see. So then it will exhibit this non-volatile property. Non-volatile in the sense that even if you remove the power, so after removing the power also it will retain the information. So it doesn't have any kind of you no need to apply the power all the time. Correct, right? So that is what we call it as a non-volatile memory. And there are other various forms of depending on the material. So we can create a different structure of Memristor. So that is required for a different application. So that we can see also in this example. So here you see the characteristics of this Memristor. This is very, very important because whenever we discuss about some new devices, obviously it exhibits new characteristics, right? If you take UJT, BJT, diode, every device has its own characteristics. Based on the characteristics only, we will come to identify. So which is whether it's suitable for this particular application or not, depending on the operating reasons, right? If you take this MOSFETs, so you're having different operating reasons like cutoff, active region, or active region, and such other breakdown reason. Like the different operating reasons are there. If you use that linear point of the MOSFET, is suitable for designing amplifiers and everything. Cutoff and saturation we can use for on and off switch. Similarly, in Memristor also, it exhibits the different kind of characteristics. If you see the characteristic IV characteristic between resistor and Memristor, you will see the different operating status. It means that depending on the voltage you apply, in the very beginning, obviously it will take some amount of time, like a diode, some knee voltage or some threshold voltage it will take, right? So to conduct, then only it will turn on. Similarly, Memristor is also. At the very beginning, the resistance is very high. Why? Because there is no conduction yet. Correct, right? So as the voltage increases, then beyond some threshold voltage, it is immediately turned on. Then current will be high. Earlier it was in high resistance state. That is what we call it as HRS. Then it will immediately turn on to go to LRS region. So that is nothing but high conductive, low resistance state. So this is how you can identify the different state of the Memristor. So then where we will find this memory property here. So that we will see. That is very interesting. I will explain it in the coming slide. So this is a little more detailed characteristics, because every device has its own maximum limitations, right? Yes. So readout circuit we will go to use like same the conventional circuit only we will go to use for that, like a CMOS circuit. Yeah, that is need to check the only voltage. Yeah, that I will come here. That I will come. I will come to that point. It will be there that you can see in this characteristic. To read what is the present information present in the Memristor. So we will apply some amount of voltage. So that is what we call it as read voltage. So then from that voltage we will go to read whether it is logic 1 information will be there or 0 information will be there. So this is how from these characteristics we will go to notice all those things. And also there is a maximum limitation. So we can't apply more voltage to your device. Every device has its own limitation, right? Because it doesn't support higher voltage. Otherwise it will burn the device. So similarly for Memristor is also limited current will flow. So that current we call it as a compliance current. So this is the maximum current flows in the Memristor. See, just like your diode, maximum forward current you studied, right? So just like that, in every device has its own maximum limitation. So from this characteristic, we will notify each and everything. So that is the benefit of why we go for this IV characteristics and analysis. So this is the very important. Now we will see in this comparison, I have kept everything. So how this is more advantageous when you go to use as a non-volatile memory. So there are other like phase coupled memory, STRAM. So there are a lot of other memories I have already compared, and you can see the energy per bit with as compared to other, and read time and write time. It is better as compared to all other memory devices. So this is one of the interesting property of this Memristor. Now we will see the crossbar structure. So this is the quite popular Memristor crossbar array. We call it as Memristor crossbar array. As the device is very small, so that we will create a crossbar array like this. So that we will create the high density memory, RAM memory. We call it as RAM memory. So this having very simple structure, and it's a very two-terminal device. And the main application comes in bio-inspired application, biologically inspired electronic circuit design, and many other applications. And obviously, in future, there are more chances that it will go to replace this conventional flash memory and everything. There are a lot of chances because technological roadmap of semiconductor published every year by IIIT Society. They are very much interesting towards this kind of new devices. They clearly mentioned the importance of these new devices for as a future candidate to as a substitute to compared to conventional devices. So they are you can go through it beyond CMOS. So it has already been published. What is next after CMOS? They already published by the IIIT. You can have a look. And also we can see this layer structure, 3D structure. Inside there is a CMOS circuit will be there, because I already told. So one of the interesting property of this Memristor is it compatible with MOSFET. So we don't have any problem. So I already told. So some certain operation, so Memristor doesn't support. Memristor doesn't have this amplification property, regenerative property. So it means that if you cascade these Memristor logic devices, the data we will lose the data. So that we need to regenerate, or we need to amplify those kind of things. For that particular part of applications, obviously we will go to use the conventional CMOS only. So that's why you can see in the crossbar array CMOS layer also, you can see it consists of sense amplifiers and other amplifiers. So that will support your crossbar array of Memristor. So that will be there. We can't completely ignore the conventional state-of-the-art devices. So that is very much essential. So this is the structure. You can see very interesting property. So I will come to this very interesting property. So this is how our synopsis looks. So this is how our Memristor looks. It is just like this is like just assume that this is one metal connected to another metal. This is another metal connected to another metal. So there is a gap between these two. So this is where all the interesting phenomenon happening inside your brain, processing and memorizing, because of this biochemical passing of biochemical messages. In biological sense, we call it as biochemical information will be transmitted. But in terms of electrical level, we call it as what? Electrochemical formation. That is almost like similar to the behavior of this synopsis. And also another important, you already know our brain is like non-linear, right? Highly non-linear. It will like, and also it is very dynamic in nature, right? So even Memristor is also have all the properties. It is Memristor is also called as a dynamic electronic devices because of its non-linear property. It means that it exhibits almost all properties of the brain. So that's why right now the most of the research scientists and all the people they're strictly focusing towards this new device because of these interesting properties. And also we can see some of the applications for bio-inspired. We call it as a bio-inspired application in the sense that whatever biologically we are right now nature has been created, we try to realize that and try to mimic the same behavior, because if you create because our overall brain consists of what billion trillions of synapses and neurons it has been. So it is having a massive, it will process the massive amount of data at a time because of its parallel processing behavior. And also you already know the brain consumes very less amount of power. Almost like so for overall brain, it will take around 23 watts of power. If you realize the same thing, it will take like megawatts in the range of 2000 megawatts like that. If you artificially create the brain, you just imagine like that. Some scientists have been reported in the article. So they mentioned that So if you want to mimic that same behavior of the brain in using the conventional devices, it's almost like it will consumes in the range of thousands of several thousands of megawatts of power it's required. 23, where is the 23 watts and where is the megawatts? Huge difference. So that is the best processor created by the nature. So here we can see how electronically we will go to mimic this behavior using this Memristor. Memristor can be almost like similar to the behavior of this synapse, and also very simple to design because of its less power dissipation and all other properties. So and also I already told less static power dissipation. So combining all these phenomena, we will go to design this using Memristor. We will go to design several applications like artificial neural networks, reconfigurable, because and also another term I can use like your Memristor is like a reconfigurable or a reprogrammable device. It means every time whenever you will pass new voltages, it will create new logic level so that it will process the data based on that, just like our brain. So here we can see we are already worked on neural networks, right? Neural networks where we need to handle high amount of computation, multiplication, addition, lot of data will be computed at the same time. And then you can see how much power dissipated by your computer when you are running the some neural network algorithm or something related to CNN or everything. So that is what the problem with the conventional devices. But when you will go to use this Memristor, we can see the structure also. Structure is also very simple. You see how they are realized. So on the left side, you will go to give your input. You go to give your inputs. Bottom, you will take the output. This is how they realize the memory. So neural network using this crossbar array using the Memristor. So if you are more interested, you just have a look at this article, then you will get more detail about this, how they realize this artificial neural network using this. And another important, one of the important area of this application is neuromorphic hardware. So I think Intel, so the Lohi, so Lohi, no, the Lohi 2 is there. So they have created this artificial neural processor. So just for they're not yet commercialized. So only for research purpose they are using right now. So it means that they created emulators to mimic the behavior of these neurons. So then they are created their own processor, that is what we call it as a neural processor. So that you can see that is very much required for this neuromorphic hardware, to fabricating this neuromorphic hardware. So for more detail, have a look. I don't think that they share the architecture, so that's why I'm not included. I didn't get any details. If they have any detail, if you can take these details and then have a look inside how they are created. So they used only CMOS devices only. Right now they are used the CMOS devices. They are not used any Memristor or memcapacitor like that. So CMOS devices only they used because they just emulated the behavior of that neuron, the neurons. Then they will combine all the neurons to create a neural processor. So that is also available. You just have a look. So that is the interesting area. So no, another you can see the other applications like already told every body cells having its own intelligence, correct, right? So we have the visual power and many sensing power and many other things. So right now the researcher are concentrating mainly towards in real world how they will go to realize. So for that they found it, this device is the most suitable, and they're having all the potential to realize all this biological behavior. So already like e-skin, brain like chip, machine vision, neuromorphic computing, there are a lot of applications they're working on right now. And bionic intelligent applications using Memristors. So in artificial intelligence, we will design robot, supportive hardware is required. So right now we are facing a lot of hurdles and complexities using conventional technologies and all. So this is going to give the lot of hopes and give the new direction to look for to design this kind of applications. Like I already told in this bionic intelligent applications also, they started using this. They already started working. So it is still at the research stage. They're not yet come to the commercialization or fabrication. So and other artificial vision and tactile sense system. So there are a lot of articles. So recently they have published the carbon-based Memristors. So the Memristor is a purely interdisciplinary field. It is not confined only particular to electronic devices. So this research will works only when you will go to collaborate with the different people who are working in material science, device physics, VLSI, computer architecture, chemistry, and all this. Then only we will go to work properly in this technology. Otherwise, it's very difficult because all this phenomena will be included. So this is the another interesting. I already told. So this is it is not like other devices. So it is having versatile properties. Already told. So one of the key property of the memristor is nonlinear behavior, right? So while taking the advantages of this nonlinear behavior, so we can use this, we can exploit this nonlinear behavior for analog application also. Mainly, memristor is very much suitable for analog processing, processing analog informations in AI applications, because it exhibits naturally, it exhibits that analog nature in the in itself. So that can be used for, already told, it's kind of a programmable resistive device. So that can be used for programmable analog circuit design and programmable amplifier, oscillators, and everything. So I will show you in my work what I have done and everything. So you will see in the later. So I have designed chaotic oscillators and many other applications. So here, what are the advantages? Because every time when you design a filter, say for example, if you want to design a filter, say for example, whenever you want to achieve different cutoff frequency, obviously you have to change what? Either resistor or capacitor, right? RC values you have to change. But in case of using this memristor, you don't need to change the resistor again and again, because it's a programmable resistor. Every time the resistive state of the memristor keep changing, so the resistance value is varying. So that can be, so that we can easily use that device for this programmable analog circuits. So that is the main advantages. Yeah. Yes. Yeah. Yeah, you can use in the feedback also. The flexibility will be there. So that is why it is called as a versatile device. We exploited all those areas, analog also, digital also, and other bio-inspired application also we exploited. I will show you that. Okay, I will show you that result also. There are a lot of possibilities. So here we can see how they realized Boolean logic. So they already successfully, they have already proposed in earlier papers. So digital application is also possible, because I already told, one is, there are two states. One is LRS, another one is HRS, right? So that I can easily exploit that property of the memristor for digital application also. Mainly it is for analog application. By making use of these two states, by changing the conductivity of that memristor, I can use for this, realizing this Boolean logic also. We are also realized some of the logic gates and Boolean function and digital circuits are also we created. We got the results, expected results. So we will see earlier what they have designed. So this is already available. So there are different logic techniques they have proposed, like you heard about in modern, in conventional, what we call it as EC, electro-coupled logic, TTL logic, CMOS logic. Different logics are there now. In memristor also, we have different logics. Like some memristor radiated logic will be there. Memristor ratio logic, we call it as MRL. Memristor radiated logic, we call it as MAT. Like that. There are different techniques of logic techniques are also available using memristor also. That also we will see. So this is what another important. So it's suitable for approximate computing, realizing Boolean function. Everything is possible using this. And another important thing is it's having a resistive switching mechanism, switching from LRS to HRS, and reprogrammable memory also. Even you heard about FPGA, right? FPGA, you already know, familiar with FPGA. It is also reprogrammable switching phenomenon. There we will go to use many other switching matrix, and there are a lot of hardware complexity inside your FPGA, right? But if we use memristor in place of that switching matrix, what we are using in FPGA, we will reduce a lot of space, lot of area, everything. So that is because your memristor is what? Reprogrammable resistive device. So we will exploit that property for this in FPGA application also. So that we what we call it as memristor based FPGA. That is also, in short, we call it as memory MR FPGA. So that is also there. We can have a look. If you are more interested, have a look. I already mentioned all the articles and all the supporting materials and everything. So now let's come to the different types of memristors. So whenever I heard about MOSFETs, I'm just taking, just to correlate with this. There are different types of MOSFETs are also there, right? Like different types of MOSFETs will be, JFET will be there, enhancement mode, depletion mode, like that. And depending on the material also, we have power MOSFETs, a lot of, depending on the material. In similarly, depending on the applications, we have different memristor types, depending on the material used. Like based on that, I can classify it like this: molecular and ionic thin film memristor. And most of the application we will go to use this ionic thin memristor. So some other specific application they will go to use this polymeric memristor. Then spintronic memristors and other things. So when it comes to molecular and ionic thin film memristor, we will see this titanic dioxide. Ionic thin film in the sense that we will go to use oxide material to realize this memristor that exhibits this ionic thin film. So and others are polymeric memristor. Polymer in the sense that is kind of plastic material, so they will go to use that material for different application. I will not explore that field. I'm just focusing only on this ionic thin film memristor. So these are all other properties like ferroelectric memristor is also there. So you heard about ferroelectric memory, all this memory, right? In memristor is also such kind of things will be there. It depends on the material. So that information I have included. Due to the shortage of time, I will not cover more about this. Okay, so this is how they are found out that interesting phenomenon in titanium dioxide. So in the why titanium is suitable for designing this memristor. So this is how they started in the year 68. So they are reported. So because your titanium dioxide exhibits a very interesting property called negative resistance behavior. So that is also very much part of that properties is required for realizing this memristor. So then later on, some people they already use that material to fabricate this memristor. Like in 2008, HP Lab already told. So they use this titanium dioxide. So later they are realized important features of this titanium dioxide. No, because of a lot of technological advancement, so people are exploiting in many materials. Material size having a huge demand right now because already exhausted with silicon, germanium, and other materials, right? So we look for new materials, so that will give better performance. So after titanium dioxide, people are exploited a lot in the material side like perovskite, chalconite, and many other materials they are exploited. They already showcased the important benefit of those materials. So based on that, they are use those different material-based memristor for different applications. So just for the sake of simplicity, I have taken only titanium dioxide. Why they are choosing this particular materials only? So that's we will see this in this because titanium dioxide is non-toxic. So that is acts as a best electrical insulator. That is another property. So then it will be so that it will be easy to fabricate. Use that material. It is easy to fabricate the memristor. So that is another important phenomenon. So then so based on this, so they have created this kind of structure. Okay. So you already know whenever you heard about oxygen-rich material, we call it as what? Like silicon dioxide. You will take whatever I will say. I will just connect to this because you can understand clearly. So silicon dioxide, right? So means that whenever you will see oxygen-rich, in the sense that it acts like a more or less like a insulator. When you reduce that oxygen property in the material, so we will make that device conductive, more conductive. Correct, right? Oxygen rich and oxygen deficit. So if you reduce that oxygen levels in the oxide, so based on that, in the same material they created two layers. One is oxygen less, 2 minus X in the sense I reduce a little bit of oxide the oxygen properties in that layer. So obviously it will become conductive, right? It will become less insulative. So if oxygen rich layer will be there, that is what we call it as insulating. It means that it is like it's not conductive. It's kind of undoped layer. So this is how the simple, just for your understanding, simple structure I have taken. It consists of doped layer and undoped layer. So the width of the doped layer we call it as W, and the overall width I call it as D. D is the overall physical dimension of your memristor. Got it? And also this W we call it as a width of the active layer. Active layer in the sense the doped layer. Okay. So this is how we can we can segregate it into two parts. One is doped part, and another one is undoped part. Doped part having very less resistance, it will conduct high amount of current. So that's why I call it as what? R on, means your device is on. Similarly, if it is very insulative, it is undoped. So based on that, I will call it as R off in the sense that there is no current flow, high resistance. So that I call it as R off. So if you combine these two features, you will get this kind of equivalent circuit. So this is how inside your memristor will happening inside your memristor. You will see when you start increasing applied voltage, you can see the more and more charged particle, or we call it as ion, because it is like a conduction happens due to this ionic drift. Okay, ions inside this insulating layer start increasing. You can see, keep on increasing. This conductivity also increases because this width D is fixed, but W is not fixed. You can vary the doped width. Doped width increases in the sense that what? It will become more conductive. So that is what happening inside this memristor. If you magnify that, you will see that when this ionic particle will reduces in the sense that undoped layer is increases. So then we can use it as off state. R off means resistance will be increases. So this is how you can differentiate. So for better understanding, you can have a look. Just for sake of simplicity, I will put forward bias and reverse bias. In forward bias, you will see the doped layer increases here, doped layer decreases. Keep on decreases. So this is just an analogy I have taken. How it will retain the different values of resistor. So you can see in the reverse current, it is just like a pipe. It will limit the flow of water, right? If the width of the pipe will be less, so then only limited amount of water will flow. If they keep on increasing the width, I'm taking this analogy just to understand how the size of this doped layer is keep on increasing, decreasing. So that is how it is happening inside your memristor. So based on that, when you apply sinusoidal wave, so this is what the characteristics I will get. So it is very important to understand that your memory, why it is nonlinear. You will get the question of why it is nonlinear. So that is the question. How I got the nonlinear property in this memristor? Because you already know in the resistor there is a current flows and voltage proportionate for the if you apply voltage, the proportionate variation in the current. But in the memristor, it is not like that. For single voltage, you can observe, you can notice two different values of current. It means that at one particular direction, the memristance of your memristor increase. At another particular direction, the memristance of the memristor decrease. It means that for the same voltage, so you have a different values. So that's how we got nonlinear property. So this is very, very important phenomenon. And also you can look at the when you apply zero voltage and when you apply zero voltage, so there is no current. It means that there is no curve here. It means that it is pinched exactly at the origin. So overall, if you combine all these properties, so I will name this characteristic as a pinched hysteresis loop. Hysteresis in the sense that we have hysteresis curve, and loop in the sense that we have a loop. So pinched in the sense it is pinched at the origin. So combining all those things, I will not go because of the time limitation. I will not explain all those things. Then you will see the material inside in the fabrication how these things will be varied. Here we can see. So there is no filament here right now. So there is no complete filament here. You can see it is empty right now. If you keep on increasing the voltage, right now it is. I'm just starting increasing in this direction. You just see, observe that this width will keep on increasing. This filament is started increasing. See, started increasing. See, so it means that there is a establishment of electrochemical filament between bottom electrode and top electrode, so that we can notice from these characteristics. See, once it will reaches the maximum current, it will completely conducted. Correct, right? Because the doped width is increased. It means that the current, high amount of current flows, and at the same time, this width remains will be same. It is not immediately it will come to actual state, but only the current will reduce. It will reduce the current, but you can see still the width will be more because of this, because it will have the non-volatile property. It frees to the particular resistance. So then you can see keep on reduce to in the other direction. So you see this layer will start decreasing. The width start decreasing. Decreasing because I'm taking in the I explained this, right? So I will just go back to the previous slide. So you will see that I already explained that. Here you will see. Here in one direction, it's a very high resistance state. When you're coming back, it is low resistance state. So that is what happening here also. So no, right now it is in which state? HRS, right? In this HRS. No, I'm going. No, it is going to LRS. LRS. No, I come to LRS. No, it is in LRS only. It is on. Once it will be on, see, it is on only. So then slowly start decreasing. It means that it is going back to HRS because it is taking in different direction. See, then there is the filament is started breaking. So it is no longer exist. So it is keep on decreasing. See. So this is how you can see understand the phenomena. Say all those important characteristic property. So this is how in the material side it looks. So based on its characteristics, so every device has its own fingerprints, right? Signature properties. The Memristor has also signature, different signatures. So this is very, very important while designing the Memristor. It means that it is frequency dependent. You can make your Memristor works like a resistor also. Possibility will be there. You just have to keep it at high frequency. It just like a linear device. It loses its hysteresis behavior. It loses its linear behavior. Sorry, non-linear behavior. Means almost it will lose its memristive behavior. So it will become like a linear resistor when we go to high frequency. So this is what we can notice. As we can see, at very low frequency, red is low frequency, omega naught. So the lobe area hysteresis have a clear hysteresis. As the frequency keep on increasing, 8 megahertz, you can see it totally almost like come to what? Linear. So these are the important three fingerprints. One is pinched hysteresis loop. Another one is at a very high frequency, it acts as a linear resistor. And the lobe area of the PHL decreases as the frequency increases. So this is what we can notice from this fingerprint. So this is very important. So there are two type kind of so you know, right? Bipolar and unipolar. UJT. In UJT you studied unijunction. So like bipolar in BJT you studied. So I no need to explain. In Memristor is also there are two classes like unipolar and bipolar. Unipolar in the sense that it only depends on the magnitude. Correct, right? It only depends on the magnitude. If that particular magnitude will be set, it will be either in HRS or LRS, irrespective of negative polarity. Correct, right? But in case of bipolar, it is considered as an polarity. If it is negative in the sense that it will come to HRS, if it is positive polarity, it will go to LRS. So that is what we will go to classify. So and other possible, I already told because of this, there are a lot of researches happening right now. So they're mainly looking towards this areas right now. So this is the hot area of research in Memristors. So in one picture, I covered everything. So in the latest article, they mentioned it. So there are important materials like I already mentioned, organic material. They're testing it with different materials. So that's why working on material is very, very important for electronic engineering. So we need to collaborate with this material science is important. And application also you can see analog calculation, logical. So right now their new Memristor is coming. We call it as a photoelectronic Memristor in the latest research. So they already published that article for photonic application and many other like artificial vision. They already started using it because they are taking different optoelectronic materials to fabricate this Memristor, photoelectronic Memristor. So these are the different material like 2D material. Right now we know that zero dimensional material, 1D material. So how we are exploiting in conventional devices. In the similar way, people are exploiting in Memristor also. So we can have a look. And no, right now we heard about Memristor and only Memristor, right? So we can extend further to two more additional components. We call it as it is a resistive behavior, memory with resistive behavior, two more properties. Memory with capacitive behavior, memory with inductive behavior. Then I got two different kinds. One is capacitor and one other is meminductor. So as you know, already familiar, linear devices like inductor, capacitor and everything. But these devices are non-linear devices and having non-volatile properties. It's not like that. So that is the unique characteristics. So that's why it is called as a new devices. And why we go for this extra meminductor and memcapacitive? Why? What is the requirement? Because we know that earlier I talking about resistive behavior phenomenon, right? So it doesn't have any kind of storage. It will store the energy in the form of it will not store any energy at all, but it will retain the information in the resistive state. But there is a little amount of static power dissipation will be there, slight amount of, but it's not like CMOS. Only a negligible amount of power dissipation will be there. But if you completely remove that power dissipation, we will go for this lossless devices. Because usually in technical world we call it as this inductor and capacitors are like lossless devices, because in general sense we call it as what, energy storing devices, correct, right? Similarly, by exploiting the same property, lossless property of that one, so we'll go to coming out with new devices called Memristor and memcapacitor, because even I can reduce much more power dissipation by using this new. And particularly this memcapacitor and meminductor purely mainly for analog, but Memristor is suitable, flexible for digital and analog. Right now, memcapacitor and meminductor, they're used for analog applications, massive parallel processing applications, AA applications. So they right now they are testing it, but till now they are not discovered the at material level, they are not yet discovered the existence of this memcapacitor. But many simulation way based and other people, they already showcased their work in some articles, but not much. So they still they are need to more focus towards this fabricating. But no, we'll come to Memristor. So right now we are commercially Memristors are available, but it is having very a lot of limitations, like no semiconductor. So it is already available, so you can directly procure and you can use for your applications. So that is the main problem is having limitations. Only at that particular temperature and only at that particular voltage we have to use. So it is not suitable for much high-end applications. So that is the drawback. And right now, whatever the article we have showed, so they have done simulation and only for restricted only for the research applications. But if you want to use it for the practical application, what is the option? So we need to emulate the behavior of this memristor and memcapacitor and meminductor. So that is what basically my work I have done. I will show you some couple of my work and you will have a look. So this is how I emulated using conventional device. I created this. We created this memristor. It will behave like more or less like a memristor itself. Why it, how it accesses a memristor? So I already told memristor is having R off and R on. Here also one is actually like R off, another one is like a R on. So depending on the frequency, because it is a frequency dependent, because you can see omega is there in this equation. I got this equation after deriving from the after the designing the circuit, we got this model, mathematical model. So then we got the results. So then we justified by performing some numerical analysis, like see this nonlinear behavior, pinch hysteresis loop, and also we can notice increasing frequency. What happens? Decrease in PHL. So that also we can notice from these characteristics. So we got it. Physical experiment and post-layout simulation also we have done. So we have got these results. It is very close to the actual behavior of the memristor. So and also so many applications, some applications also we have used. We exploited our memristor for digital analog and some bio-inspired applications and nonlinear applications like chaotic oscillators. Everything we have designed. So these are some experimental results we have got using the discrete components also. Same topology we realized on breadboard and we got the same results. And so a lot of because the MOSFETs what we are used, so having some in reality obviously having some side effects, right? We call it as non-ideal effects, because due to that the shape of the curve will get little bit having some discrepancies compared to the numerical analysis, and also because due to we are using different type of discrete MOSFETs we are used here in our experiment. So that's why the shape is different as compared to this. So why our proposed? So earlier a lot of people have designed that. No, right now people have proposed many much more better optimized one. So this is what the work we have done earlier. So you see the hardware, how many components they used. So how we fully optimized that. So we fully optimized. I am almost come to the end. So it consists of only 4 transistors and 1 MOSFETs. Even our work is without MOSFET also, and we achieved frequency up to here. So similarly, we got a meminductor, and meminductor behavior, it's having it depend on the time integral of flux. It is a relationship between time having the relationship with respect to the current and time integral of flux. So that's what we call it as time integral of flux. So what is this mathematical model represent? Whenever you find the integration, it having memory, right? It keep on accumulating the previous results, past history. So that is what meminductor exhibits this property, memory property, by showing in its mathematical model. It exhibits non-volatile behavior or memory behavior. So this is how we realize the same structure, same mathematical model using this meminductor. You can see we used VDTA and OTA. So we proposed, and also we can have a look, in the article. It's already available, and we already explained. So because of the limited time, so I'm not able to cover the technical details. So this is how we realized. And then we got this rho of t is nothing but what? Time integral of flux. So in the proposed circuit, so what should be there? Time integral of flux. In the ideal model also, time integral of flux will be there. So this is how we verified successful implementation of our meminductor. So results also we got. Almost meminductor and memristor are having all the same characteristics. But only see is in the memristor is relationship between current and voltage. Inductor is a relationship between current and flux. Very good. So this is what the difference. So this is the post-layout simulation, experimental analysis, and also we can see we fully optimized, and it is more both power efficient area, and also we can able to use this device for high frequency application also. So this is what the chaotic oscillator. So this is the very interesting nonlinear circuit application. So because when you want to secure your information, like especially secure communication, cryptographic, you need chaos. You need to mix your information with the chaos, right? So for that, this nonlinear device, especially this memristor, meminductor, going to be very useful for this application. This is why it is called as versatile. We created this chaotic oscillator also. For different parameters, we got different chaos. See the pattern. It is varying because of different conditions. So similarly for capacitor, there it is time integral of flux, here time integral of charge, because capacitor related to charge. There inductor related to flux. So this is the difference. So how we will go to realize this? Similarly, we created this. So we got, and also we can see sigma of t is nothing but time integral of charge. We got it in our circuit also. We derived it, and it is very much similar to our ideal equation. So we got it. So we have verified this, and also very interesting. So this is the first time we have. So in our we got this interesting results in our circuit. So successfully we created this adaptive learning circuits. So here we are mimicking the behavior of unicellular algorithm called amoeba. So how amoeba will behave, how it will change its locomotive speed based on the external events like temperature, humidity, like that. Similarly, we created this and we got this. So this is what all about we can have a look. So thank you. Thank you so much for your kind attention and your patience. So thank you. So firstly, I would like to thank entire Samvaad team for making all these arrangements and taking time for all those things. And also all the who are all present here. Thank you for your kind attention and valuable time. Thank you.
Hello.
Yeah.
Like mostly you said that it can be used as an replacement or an alternative for CMOS circuits as well.
Yes.
So for example, if I'm designing a five-stage OTA, which acts as a two-stage op-amp, in that case, all my parameters are fixed. For example, the phase margin, gain, everything. So can we use memristors to make all that parameters dynamic as well?
But we only some particular places we can replace the MOSFET with memristor. Possibilities are more. We can do that.
Okay.
Article also we can see many people they have created differential amplifier using memristor, and everything will be there already there. It is possible.
Okay.
It will work, and we will make that overall circuit dynamic.
Because for example, if I'm using an op-amp, it's if I'm not using a practical op-amp, the gain is always fixed.
Yes.
So we cannot change the gain. Like if you have to change the gain, then simply we have to change the from design perspective, W by L ratio and everything.
Yes.
So I was like, my question was, can we use memristors to make dynamic op-amps also, that if we give a certain frequency, I get a certain gain.
Yeah, we already people have done. They have created a lot of oscillators, filters, amplifiers, and everything. So we can do that. So that is also one of the other possible side of the memristor. So in that application also we can exploit. So but we can't fully replace the CMOS. But
so what are the major drawbacks of not able to fully replace CMOS?
So I already told you, right? Memristor is a passive device. It doesn't have that amplification ability.
Yeah. So that's why that's why we cannot use it directly for amplification purposes.
It is mainly meant for the computation.
Okay.
So that parallel processing,
like MOSFETs and BJT, they have that amplification property in their transistor. Like when they're in saturation, we use them for amplification.
That's why I showed in the characteristics. I have not showed any amplification.
Yes.
So that's why the characteristic is very, very important to identify whether my device is suitable for the amplification or not. It shows only non-volatile and nonlinear property. So that is the main point.
Thank you, sir.
Yeah, my question is regarding the pinched hysteresis loop. So anytime in any system, let's say, if we see a pinched hysteresis loop, can we say that it has memristor-like properties? I mean, or there are other systems in electronics which show similar properties as well?
Yeah, that's what I showed in the fingerprints, right? So pinched hysteresis loop is not only the parameter to judge whether the device is memristor or not a memristor. So,
okay, so if it satisfies those three, even if, say, we are looking at a biological system or some other system, and it's not a electronic system where I know it's a memristor, if I see all these three properties, I should be able to say that it has
and also
memristor-like properties.
Yeah, we can say that approximately. We can say that.
So there are no other electronic systems which shows similar properties, like at least none that you're aware of.
Yeah, there are people already they have showed that. So whichever the devices which exhibit pinched hysteresis loop, they will say it as the memristor. So you can see in my example only, I used MOSFET, but it is giving that PHL pinched hysteresis curve. I can use as a memristor only.
Okay.
Even I used for different application, possible application where memristor can also be used, and I got the same results. What I can use by using the real world memristor, same result also I got.
Okay. And another question I had was regarding the chaotic circuit. So in the circuit that you designed, does it has, I mean, is it just a memristor or it also has memcapacitor? And can you just go back and show me the circuit once again, please?
You can get that chaotic oscillator.
Sure.
So you can use either memristor, memcapacitor, because only the requirement for my designing chaotic oscillator is at least one device should be nonlinear. Yeah. We tested for both. Memristor also we got the result. Yeah, there also you can use. Yeah, because both having that property, no? So I can exploit that nonlinear property and memory property. Yeah. Yes. We will get. Yeah, there are already a lot of articles. They already validated the results. But depending on the application, you need to change the material also. But for artificial visual recognition, and it varies from different application to applications. Because that is what the main thing, no? Because in one device we can't expect everything. So that is the main thing. Yeah, we created the we just emulated the behavior of those Memcomputing devices. So we designed a possible applications, like we got the results. It works because main thing is required is non-volatile property and non-linear property. So that is what in nature also works, no? Dynamic, analog, non-linear behavior. So that's what. Thanks for your question. Thank you.
Two questions, but very basic ones. Yes, so we can cover it in under a minute. Yeah. So one is you mentioned about how easy it is to fabricate a memristor compared to any other kind of MOSFET device. But you also mentioned in your presentation as to due to complexity, it has not been implemented. So that seemed very.
So the main problem with right now the fabrication process is whenever we'll go to fabricate below 10 nanometer, we need to change the entire fabrication process. We have to use different mask layer. Etching process will be different.
So the granularity is much finer for memory.
That is the main problem. So that's what because we need to change the entire fabrication plant. So the process, what's the technology right now we are using? So that doesn't support. So that is good.
The other is, so at high frequencies, you mentioned that the memristor is showing almost a linear kind of behavior. But you also mentioned about enabling high speed readings. So is it suitable? What kind of, for example, if we take a laptop, then where is this suitable? Is it suitable as a RAM or is it suitable for memory? Because the SD card or the RAM, if you see, we're going to read a lot of reads and writes continuously. And if it's going to be at high frequency and it is going to behave like a simple resistor, then it's not very useful. So those two items also.
So actually the switching from one resistive state to another resistive state, that is purely for digital side. But whenever I will go to use for analog applications, so I will apply external frequency. Here,
okay, we're only talking about the digital application, and in digital application, there will be applications which require high frequency switching also. Right? So in that area,
we can design the particular memristor that will support the high frequency. So that's what we have done. Earlier, it will support up to kilohertz. Now we designed up to megahertz.
3 megahertz. you've designed.
Even our memcapacitor is working up to 24 megahertz. We can go there. You can still, we can like that, if you keep optimizing and keep incorporating some much more efficient circuit element, you can achieve high frequency also. You can, so that you can use that device for high frequency applications.
Got it.
So that is what we showcased it in our work for high frequency applications. But still, their possibilities are more. Still, there are a lot of things are there we need to work.
Thank you, sir.
Thank you.
Thank you very much, sir, for the interesting session. I know now everybody here know about Memstar, and it was a really.
So that's what my intention. So if I will share these insights and everything, so they should get some any insights. So they have to take it forward. Then they have to apply their own idea. They will coming out with some innovative solutions. So it will be better. So that's why it is always good to share information and know about new technology. It's always good. Thank you all.
Thank you so much. We conclude.